Welcome to This Explainer, everyone. I'm going to be your time-traveling professor for today, and together we are going to step back through the centuries to explore the invisible, rhythmic patterns that secretly govern our universe. We'll be looking at everything from the smallest vibrating atoms to the grand, sweeping orbits of planets as we unpack the physics of oscillations. By the time we wrap up, you'll be fully equipped to absolutely conquer your physics exams, and honestly, you'll start seeing the world through an entirely new, rhythmic lens.
Okay, let's dive into our syllabus for today's intensive study guide. We're going to cover the pulse of the universe, learn the language of rhythms, travel back in time to 1581 with Galileo, analyze energy states, look at some real-world applications, and finally, we'll test your knowledge with a final exam review.
Section 1. The pulse of the universe. Let's look at periodic versus oscillatory motion.
To really understand oscillations, we first have to understand periodic motion. Any motion that repeats itself at regular intervals of time, that's periodic. Think of a kid bouncing a ball off the ground. The ball falls, hits the ground, and bounces back up. It repeats. But here is a classic exam trap, so pay attention. While that bouncing ball is periodic, it is not oscillatory. See, oscillatory motion requires a body to move to and fro about a specific mean equilibrium position, kind of like the pendulum of a grandfather clock swaying back and forth across a central point. Remember this absolute rule for your exams. Every oscillatory motion is periodic, but not every periodic motion is oscillatory.
Moving right along to Section 2, the language of rhythms. Let's master our oscillation vocabulary.
First up is the period, represented by a capital T. The period is simply the smallest interval of time after which a repeating motion completes one full cycle. Think of pushing a child on a playground swing. The period is the exact amount of time it takes for that swing to leave your hands, go all the way forward, and come all the way back to your hands. And while the standard unit is usually seconds, periods can vary wildly in some pretty amazing ways, from mere microseconds for a vibrating quartz crystal, all the way to 88 Earth days for the planet Mercury to orbit the Sun.
Next is frequency, which we represent with the Greek letter nu. Frequency is just the flip side, the reciprocal of the period. If the period asks, how long does one cycle take? Well, the frequency asks, how many cycles happen in exactly 1 second? It's measured in a unit called hertz. And yes, that's named in honor of Heinrich Hertz, the brilliant physicist who actually discovered radio waves. 1 hertz simply equals 1 full oscillation per second.
Let's ground this math in reality. Actually, go ahead and take your own pulse. An average human heart beats about 75 times in 1 minute. Since a minute is 60 seconds, if we divide 75 by 60, we find the beat frequency of the human heart is 1.25 hertz. And if we take the reciprocal of that number, we find the period of your heartbeat is exactly 0.8 seconds. You're literally a walking biological oscillator.
And this brilliantly illustrates our third major term, amplitude, denoted by a capital A. Amplitude tells us exactly how far our oscillating object pushes its boundaries. If we go back to our playground swing, that central resting position where the swing just hangs straight down, that's the mean position. The amplitude is the absolute highest point that swing reaches in the air before gravity pulls it back down.
Section 3, Galileo and the pendulum. Let's dig into the history. For literally centuries, ancient thinkers observed repetitive natural cycles with mere curiosity. They noticed them, sure, but the major shift to formal scientific understanding actually began in a church in Pisa back in 1581. A young Galileo Galilei was sitting there, watching a heavy chandelier swinging back and forth from the ceiling. He really wanted to time the swings, but watches didn't exist yet. So what did he do? He used his own pulse as a rudimentary stopwatch, and he discovered a shocking truth. Whether the chandelier was swinging in really wide arcs or very narrow ones, the time it took to complete one full to and fro swing remained exactly the same. This revelation laid the entire groundwork for the formal laws of simple harmonic motion. Let's walk through the actual mechanics of Galileo's pendulum to see why this happens. Imagine a bob of mass m suspended by a string. When you pull it to the side, giving it a small angular displacement, gravity gets to work. The force of gravity resolves into two components, but it's the tangential force that creates a restoring torque. This force constantly tries to pull the bob back to that center mean position. But as the bob reaches the center, its inertia just carries it right past the equilibrium point, up the other side, until gravity finally stops it and pulls it back again. As long as that initial angle is small, this back and forth dance is the perfect embodiment of simple harmonic motion.
Section 4. Energy and circular motion. Let's look at how we map these harmonics mathematically.
Now, what's really interesting here is how physicists visualize these equations. Imagine you tie a ball to a string and swing it around in a perfect horizontal circle. That right there is uniform circular motion. But if you shine a bright light on that ball and watch the shadow it casts on a wall, that shadow is moving in a straight horizontal line. It speeds up in the middle and completely stops at the edges. The projection of uniform circular motion on a diameter is exactly simple harmonic motion. This is how we map circular paths onto linear displacement graphs to help visualize the math you'll see on your exams.
And as that shadow moves back and forth, its energy state is constantly shifting. When a pendulum or an oscillating spring is all the way at its extreme edges, the maximum amplitude, it briefly stops moving. At this exact moment, kinetic energy is zero, and potential energy is at its absolute maximum. Then, as it rushes back through the center equilibrium position, it reaches its top speed. Here, potential energy drops to zero, and kinetic energy is totally maxed out. So the crucial point to remember is that throughout this entire shifting dance back and forth, the total mechanical energy of a harmonic oscillator remains completely constant.
Section 5. Real-world vibrations. Let's look at oscillations in everyday life.
The physics of oscillations isn't just restricted to church chandeliers. It is quite literally everywhere. When you strum a guitar, the string vibrates, and the surrounding air molecules oscillate, propagating a sound wave straight to your ear. On a microscopic level, atoms within solid materials are constantly vibrating in simple spatial patterns about their equilibrium positions, and the average energy of those vibrations is what we actually feel as temperature. Even the AC power supply in your home power outlets is an oscillation, with the voltage continuously dropping positive and negative about a zero mean value.
Now, for your exam, don't worry too much. You are primarily going to deal with perfect linear harmonic oscillators, where the restoring force is perfectly and directly proportional to the displacement. But in the messy, real world of nature and heavy machinery, forces aren't always so neat. Real machinery often acts as a nonlinear oscillator, where the restoring forces contain small, complex, additional mathematical terms that complicate the overall motion.
But wait, what happens if you push a child on a playground swing and just walk away? Well, in practice, oscillating bodies eventually come to rest at their equilibrium positions. This is because of damping forces, primarily friction and air resistance, which slowly dissipate the system's mechanical energy. Unless some external periodic agency keeps pushing, every real-world oscillation will eventually just fade away.
Section 6. The final exam review. Let's test your knowledge.
Here is your ultimate, intensive study guide checklist for simple harmonic motion. If you are asked to identify SHM on a test, you need to check for these 4 things. 1. It must be an oscillatory, periodic to and fro motion. 2. There must be a restoring force directly proportional to the displacement. 3. That force must always be directed towards the mean position. And 4. The displacement over time can be perfectly expressed as a sinusoidal mathematical function like a sine or cosine wave. Okay, let's see how well you've absorbed this with a final practice question.
Here is your final summary quiz question on period and frequency. Imagine a simple pendulum whose length is perfectly adjusted so that it ticks seconds. This means it makes one single tick every time it swings from one side to the other. What is its total time period for a full oscillation? Think back to our definition of a period for a second.
The answer is 2 seconds. Remember, a full time period is the time required for one complete to and fro oscillation, returning exactly to the starting state. So if a swing from left to right takes 1 tick, or 1 second, then the return swing from right to left has to take another second. Therefore, the period of a seconds pendulum is exactly 2 seconds. So we've seen how early scientists transformed mere observational curiosity into the formal laws that map the changing energy of our rhythmic reality. If the universe is fundamentally built on these invisible oscillations, from the warmth of vibrating atoms in a solid desk to the beat of your own heart, it leaves us with one final thought. What profound rhythms are you currently failing to notice in your own daily life? Keep observing, keep studying, and good luck on your exams.